Can you hear me, everyone in the room? Yeah. Okay, I guess we'll get started with this course. It's 1 minute past, so anyone else that's finishing coffee will just come in. So yeah, welcome back to Differentiable Programming course. This is the second session. We're going to be using almost the same setup. So it's the same repository, which I've put it in Slack. It says Differentiable Programming Summer School 2025. It's been updated since yesterday so that the environment is slightly different. So there's an extra automatic differentiation tool that's going to be included. The reason we didn't include it yesterday is it comes with quite a bit of memory. So the code space might take longer to boot up, but hopefully the install will be smoother. So it's the same thing as yesterday. Click on the green button for code, click on code spaces, and then create the code space on main. As you can see, I've already got one running. And it will put you in a VS Code session and you'll see the README. And as yesterday, you have to start out by typing source install, which I've got at the bottom there. It will set everything up. It will set things up slightly differently. So it's going to, in addition to installing Tapenade, it's also going to install Firedrake, which is a finite element library, but it comes with its own automatic differentiation tool that we'll be using today. So I'll let people sort of have a go at that, Sam.
So should I create a new workspace?
Yes, that's a good question. So people might still have a code space lying around from yesterday. I think it does automatically delete, but I don't know how long it takes for that to happen. So I would recommend deleting it. So for example, looking at mine, there's 3 dots. And then if you scroll to the bottom, there's delete. I won't do it because I'm using it. But there's also options to stop it or delete it. I think it will have auto stopped if you've just not been using it. But I'll delete it if I were you, and then start a new one, just because the environment's going to be different. And what was the other thing I was going to say? Yeah, we've actually now got a web page version as well that Nicola has kind of set up. So linked from the repository, there's this web page here where you can go there, and there's a bit of a sort of overview, and then the 2 notebooks are available in a HTML format. So they're not executable, but you can just see the contents as you scroll through. So this was for yesterday's notebook, for example. And I think the detailed stuff does still work, so you can still do some of the exercises that don't require coding and then check your answers. So yeah, I'm aware that the code space might take a little while, so we'll probably just get started. But if anyone's having a problem with code spaces or anything else, then just put your hand up and we'll come and try and help out. So once you have your code space and once you've done the install, I've already done mine, so I won't run it again. Similar to yesterday, we'll see that there's 2 sessions, session 1, session 2, and then within session 2, we've got a different notebook now, which we've been open, and we're going to run through that. One of the differences with the environment is that there's no longer a virtual environment. Firedrake just sort of install everything into the system on this particular environment. So when you run the first cell and you choose your Python environment, it will be very easy because there's only one choice. You don't need to worry about picking the wrong one because they're all the same. And eventually that should hopefully work. So as you can see, we just import various things similar to yesterday for plotting, NumPy, and then there's this tool PyAdjoint, which we'll come to later. Okay, so yesterday was about forward mode, and it was about source transformation tool called Tapenade. Today we're going to see a different approach to a different mode of automatic differentiation called reverse mode, and we're also going to find out about a new tool. So a new approach to these tools, which is called operator overloading. So there's a bit of motivation. Hopefully you were sufficiently interested in yesterday's session to put you here, so that's a good start. But it was a little bit unclear how to make use of differentiable programming in practice, so we'll sort of hopefully give a better idea of that today. we computed first order derivatives for various programs, but in some advanced applications, so for example, certain implementations of uncertainty quantification, you need Hessians, which Hessian is a matrix of second derivatives. So how do we compute those with AD tools? And another question is, well, in the last session, we just learned a lot of stuff about training neural networks in PyTorch. And Isaac mentioned that you implement the forward method, but you don't implement the backward method because it happens automatically. So this is where automatic differentiation is happening in PyTorch. They have their own backend for that. And in this session, we'll learn a bit about how that actually works under the hood, hopefully. So just to sort of motivate that, I've got an image of a neural network here, the kind of thing that we would be training. And effectively, training a neural network is just like solving an optimization problem like we saw yesterday. So you've got a load of parameters that you want to optimize. So that's all of the weights associated with the nodes in the network. And then you've got this, the output is effectively the value of the loss function. So as yesterday we saw that we optimize a parameter in a model, so there's this theta parameter, in order to minimize the cost function. When you have a neural network, effectively all you're doing to train it is to minimize all of these different weights. Optimize these weights so that the loss function is minimized. So yesterday we saw this case where there was a single parameter and then there was this cost function. But this is a very, very simple example of a neural net. And in more realistic examples, you're going to have way more degrees of freedom than this. So you've only got one output, but you've got like millions or billions of things that you're trying to optimize. And as we saw yesterday, when you run forward mode for like if you have multiple different inputs and you want to get the derivative with respect to each of them, you have to either have a seed vector for each of those inputs, or you need to have this clever choice of in a sparse case, you can have a clever choice of seed vectors such that it's a smaller set, but you still need to do multiple JDPs. And when we look at this, it's a fully connected neural network, which I know is like the most basic thing you do, but this is not a sparse structure. This is very dense because everything's connected to everything, or at least as you go through layers, everything's connected to everything. So it's unlikely that we can do very much compression on this kind of network when we're doing the differentiation. So if we want to compute gradients that we need for the neural network, we're going to need to do loads and loads and loads of JVPs in order to get the gradients that we need. Hopefully that makes sense to people, based on what we learned yesterday. So it doesn't really seem like a great fit. I think we need to do something different. Like, is it possible to configure AD in a different way for this kind of training? So the learning objectives for today, as I said, we're going to learn about reverse mode, we're going to learn about operator overloading, and we're going to compare them to the forward mode and to source transformation that we saw yesterday. We're going to verify the consistency of tapenade in both the forward and the reverse mode cases using something called dot product test. We're going to look at higher order derivatives with tapenade. And then once we're confident with the reverse mode, we'll move on to this operator overloading type of AD tool. And that's called PyAdjoint. So we'll see some basic usage of that and then some showcases of some more advanced usage for sort of real research problems. And then if there's time at the end, we'll look at checkpointing, which is something you need to worry about when you're doing large-scale problems. Has anyone managed to get the code space running yet? Yeah, a few people? Okay, that's good. We're not going to need it for a little while, but it's good to hear that people are able to connect. So just to recap on yesterday, we're going to use this term AD, automatic differentiation, differentiable programming, similar sort of thing. We use this notation for derivatives that we saw, f prime and df by dx. And we noted this x dot. Unfortunately, I forgot to fix the math rendering here, but we can view it. Let's just go back and view it. Oops. Sometimes things render well in a local Jupyter instance, but not in VS Code, in code spaces, which kind of confuses me. But this is my local version. So yesterday we saw this notation x dot for the forward mode derivatives and also for the seed vectors that you use for forward mode. Now that we're in reverse mode, you use a different notation. And for one reason or another, the notation that's used is a bar. So when you have like if the variable is y, then we put a bar over the top. And again, there's some caution. This does not mean a mean value. This is either a reverse mode derivative or it's a reverse mode seed vector, depending on the context. So hopefully that'll be clear as we go through. But yeah, if you see a bar on the top of something, it will never mean mean as far as this notebook is concerned. And yesterday we saw that when you have derivatives in code, you have this underscore d. For reverse mode, similarly, we have underscore b. So you can compute derivatives using these two different approaches, but the code that implements those has these two different notations. And come back here. We had a bit of history of forward mode yesterday, so history of reverse mode. I should note that it's also called backpropagation, which maybe rings a few bells for people. Backpropagation. It's kind of interesting. So as I said, like automatic differentiation's got in and out fashion, and it's sort of had its highs and lows over the years of popularity. Also, for a long time, it was called reverse mode because that's what they even community called it. Whereas now people tend to call it backpropagation because of the machine learning community, because that's what they call it. It was actually called backpropagation first, interestingly. So this was, in 1962, Frank Rosenblatt named it as backpropagate, or used the term backpropagating error correction. As we heard yesterday, didn't actually know how to implement this using what was available then. And steel penning is a name that we'll hear quite a bit in this notebook. Bert Steele Penning introduced the modern formulation of reverse mode in the late 1980s, and this is an image from his PhD thesis, with a sort of sketch of this software called Jake, which was designed to do this reverse mode differentiation. So you can see it here as a program, written Fortran, of course, so we're still using Fortran now. And then this idea that you can compute the derivatives. So yesterday we saw that forward mode is all about this Jacobian vector product. So we're computing the matrix vector product of the Jacobian evaluated at some input on the C vector, which is the direction. So it's like a directional derivative. And again, on its own, grad F is just its coding. And the forward mode of AD does this in a sort of matrix-free manner. So you don't actually need to know what the Jacobian is in order to compute this, but we've had to play around with some different methods for computing the Jacobian itself by choosing the C vectors in an appropriate way. So in the reverse mode, we calculate something slightly different. So we actually have the Jacobian transpose vector product, or JTVP, as opposed to the JVP. Although I'll try not to use that acronym because it's quite hard to say. So what is the JTVP? Well, given some function f that we want to differentiate, given some x that we want to evaluate it at, we have now a seed vector y bar. So as I said, the reverse mode, the seeds have a bar notation. This is still a direction, but it's a direction in which we want to compute the transpose of Jacobian. So it's almost exactly the same calculation. It's just that we have a transpose of this derivative. It'll become clear later, hopefully, why it's useful to do this. That you can just for now just take it on board. This is what we're going to be able to compute. And there's an optional exercise there for you to convince yourself that this is well defined in terms of the different dimensionalities of these quantities. Yes.
Tell me, was that something like an integration C vector?
It's a good question. So what the question is, what's the intuition for the C vector? So when you've got JVP, it's the direction in which you're computing the derivative, whereas now I guess it's well, I guess it's the tangent, not tangent, perpendicular to the direction that you're computing the derivative. Yeah, I guess I'm not too great at geometric interpretations, but you'll see some computational reasons why you want to do this. Again, it's matrix free, so we don't need this Jacobian itself necessarily to compute this product. So this is hopefully where it starts to become a little bit clearer. So we've got these different C vectors. We have these different quantities that we can compute with forward mode and reverse mode. The computational reason that we do this is that, as I mentioned before, forward mode works well when you have a small number of inputs. But inputs here means parameters that we're computing derivative with respect to. So if there's a small number of inputs, or the number of inputs is much smaller than the number of outputs, that's what this notation here means, then forward mode can do a very good job. So if there's only one parameter that you're tuning, it doesn't matter how many outputs you have, you still only need one JVP. Because you take the same program, you take a single seed vector for that one input, and no matter how many outputs there are, the dimension of your gradient is the same as the dimension of the output. So an example is sort of optimization with respect to a small number of parameters. So we saw that yesterday, optimization with respect to one parameter, very small number. Sensitivity analysis can be another one. So if you've got a model that has some uncertain parameters in it, if those uncertain parameters are single numbers, then you can do a sort of study that sees how, if they vary slightly, how does that impact your outputs. Reverse mode is the opposite. So it's more appropriate if the number of inputs is much larger than the number of outputs. So the example we just talked about before is machine learning training. So you've got a loss function that's just a single number, and you have lots and lots of inputs. And as it turns out, you only need to do, well, the maximum number of JTTPs that you're going to need to do is the number of outputs. So if there's only one output, then you can compute the gradient with respect to all of the inputs at the same time with one JTTP. So this is the real power of reverse mode. It's the machine learning, basically. You can compute gradients with respect to as many inputs as you want in a single call. So other examples are, like we saw yesterday, when you have ODE constrained optimization or PD constrained optimization, again, you tend to just have a single output. It's a scalar cost function. So that's another good candidate. And then for some more advanced stuff, goal-oriented error estimation. There again, you have these quantity of interest that typically are just scalar numbers. So I think the main motivation for choosing between the two approaches is the dimensionality of the problem. Forward mode is computed eagerly. So we saw yesterday, when you compute the gradient in forward mode, you also compute the primal code. Whereas in reverse mode, you can't do that, unfortunately. So you actually need to run the primal code before you run reverse mode. You need to go forward before you come back. And related to that, it turns out that for reverse mode, there tends to be higher memory requirements as well, because we need to store sort of trajectories. We'll come back to that later, but that's just something to be aware of. So I've realized I've talked quite a lot. So has anyone got any questions about any of this? Has anyone not got their code space working?
Right, I got mine.
That's fine.
It's catching up.
But if you have any problems, we can put. So if everyone, yes.
Yeah.
Anyone else got any issues with code space? Okay, well, we'll have a bit of time once we go into the exercise anyway. We're going to revisit the sort of hello world example from yesterday. So we've got this F and G example where there's two functions. One is the product of two arguments, the other one is sine and cos. So hopefully you all remember that. And we saw that there's this directed acyclic graph interpretation of the two functions. So you've got one of them has two arguments mapping to one, the other one has one argument mapping to two. You can see these sort of code paths almost of like what happens to each of the arguments. And we saw that with forward mode, the gradient information propagates through the graph in forward direction. As you might expect, it propagates in the reverse mode through the DAG in reverse mode. So in this case, for this composition of functions, the seed vector that we have is related to the output, and the output is called Z. So we have Z bar, which has two components, Z bar 1 and Z bar 2. And so when you propagate through the reverse mode of AD, you first have to get the derivatives of sine and cos. And then you have derivatives, well, sort of like the Y bar. And then you need to differentiate through the multiplication by x2 and x1. And noting again that these are partial derivatives. So when you do the differentiation with respect to x1, we're holding x2 as constant. So that's just like a scalar number. It's not a variable. And if we do that, then we get these derivatives of x bar. So it's just a sort of sketch for people that prefer a more graphical view things. And then the code for the functions, again, we can find it in this. You look inside exercises and then FG, then we have the same functions as yesterday. The only difference is that we've put them in modules to be to use slightly better for Fortran programming practices. So there's this module which is kind of like a Python module in the sense that you can import from it. And there's just one subroutine called F, and this is exactly the same code we saw yesterday. And similarly for G as well. And my exercise to you is to go to this location. So you'll need to go, make sure that you've done this source install, by the way, for anyone that lists that, source install.sh, which will set up your environment. And then once you're ready to start the exercise, you go session 2, exercises FG. And oh, interesting. It looks like it's kept some stuff in. Make clean. You should see a few Fortran files, a make file, and the exercises are firstly to just run tappernab-h to review the options. So this is exactly the same as yesterday. There's a question, but let's be 1 second. And then the exercise is to now apply tappernab to each of these in reverse mode. So you'll need to have a look at tappernab-h to see how you do that. And you should create this F mod B and G mod B. And unfortunately, because we're dealing with modules, you have to specify how to name the file that comes out. Because by default, it'll put _diff, whereas what we actually want is _b for consistency with some of the later exercises. Good question. Yeah.
Yeah, so you said you're differentiating in reverse if you graph. Are you integrating?
No, so it's not integration. That's a good question. So the question was, since we're differentiating in reverse, is that integrating? No, so it's all very, it gets quite confusing. So it's not really an inverse in the sense that integration is the inverse of differentiation. It's more that it's the transpose. So like we were kind of discussing before, the interpretation is that instead of computing a derivative in a particular direction, you go like perpendicular to that direction. So you can still compute exactly the same things, but just in a different way. So that was like I was saying before, you get, when you want to use AD, you choose, do I use forward mode or do I use reverse mode? And depending on the problem, one's more suitable than the other. But you can always get the same thing out. You just might need to formulate things in something. Any other questions? If not, yeah, we can leave like 5 minutes or so to work on this exercise. If you've got any questions or concerns, put your hand up. Yeah, we were just having a discussion there about what the forward and reverse mode mean. Actually, the seed vector is actually this. It's the same concept. It's just that you're implementing it a different way. So if we think of this here, so we're computing the derivative of f in the direction x dot, then when you compute the JTVP, you're still computing the derivative in the direction y bar. It's just that you compute it in a different way, basically.
So it's in the form,
different
and
space.
you take all the individual Cartesian vectors in each direction, and you compute each component of the gradient in forward mode. And if you want to have it in one direction, you take the backward mode and you multiply it gradient with this direction, and it gives you a number.
Yeah.
In this, so direction and gradient is a little bit.
Yeah. Yeah, no, it's quite tricky.
So the gradient by itself is also a direction.
Yeah.
But the other one is you want the derivative in a special direction. It had nothing to do with the gradient. It's the derivative in a direction.
Yes.
Should the direction be the same for both of them? Just how you're going.
Yeah, exactly. Exactly.
Get in the game.
Yeah.
Something
So
like
if you want the partial derivative with respect to the first component of the output,
Yeah.
then you still pick 1, 0, 0, 0, 0, 0.
Yeah.
something in differential geometry.
Thank you. Yeah, no, sorry for the slightly unclear geometrical interpretation. Oops, sorry. Yeah, so we've had a bit of time to do this, so hopefully people manage to do some of this exercise. So if we tap on our -H again, we see all these different things. So yesterday we were using tangent mode or -D, and this was just, as you can see, it's the default. So we didn't actually need to specify this, but if we put -D, then we would be using forward mode. Today we're using reverse mode, so we need to specify either -reverse or -B. Yesterday, if you recall, we also saw the vector mode, which you can type -multi for, and we also saw this head option, which we're going to be using today. Again, we also saw yesterday there's this tangent module name, which we needed to use because by default it does _diff rather than _d. And today, as was noted in the hint, tangent mode is another term for forward mode, and adjunct mode is another term for reverse mode. So there's this adj module name you need to use so that you get a better model extension. There's loads of other arguments we're not going to use, but feel free to ask if you've got any questions about those. And then for the actual computation, we go to the FG subdirectory. You can see what's there. This is not one of the it seems, but there's a few things. And then you can put tapenard, now we've got -B, as I've mentioned, and then head. And the head is going to be the same as in the forward mode, because you still have the subroutine that we're interested in, which is F. You still have the independent variables, which is X. And you still have the dependent variables, which is Y. It's just it's going to be computed in a different way. And yeah, apologies again for the fact that this notation can be used either way if you switch the slash to a forward slash. But I think if you play around, you'll get to the right answer eventually. And then we put add module name B, F mod, and you should get this derivative code that's generated. So just comparison, this was the primal code, so we just have the product. And then when we look at the derivative code, it's got the primal at the bottom with some formatting, and then it's also got this reverse mode derivative. And this looks quite different to what we saw yesterday. So just for comparison, let's also get the forward mode derivative. So we need to change this to tangent module name. We need to use the -D rather than -B. That will generate what we already had yesterday. And if we open that, then you see that the forward mode derivative looks a lot like what you might expect from applying the product rule. from A level maths. So you have the one component times the derivative of the other, and then you have the other component times the derivative of the one, sort of thing. And then there's also this eagerly evaluated computation, whereas in I didn't double click it. If you double click these things, then they stay open. In this one, it looks a little bit different. So we've got, I mean, firstly, in the first one, X and XD are inputs, right? And Y and YD are outputs. Whereas in this one here, X is an input, so you can see it's got intent in. Unfortunately, you don't have to always specify whether something intent in or intent out. The Fortran it will just pick up things by default, and so Tapenade doesn't seem to do this. So it's a little bit confusing to check exactly what's going on here. But as you can see, XB is an output. Well, it's both. Is it an output? Is it both input and output? But it's being set to 0 there, and then it's being incremented basically. And YB is the seed vector now. So it's not as simple as just the first two things being input and the second two things being output. Now we've got X as an input and YB as an input, and then XB is an output and Y is an output. So a little bit confusing. But if you look at this, then for the first component of this XB, it's kind of just what you would expect, because you've got the first component and you multiply it by, just multiply that by the second component. So if we look at this graph again, the reverse mode graph, when we go, we're computing the derivative for the first component. So we take the seed vector for Y, and then we follow this left-hand trajectory. And what does that involve? Well, it involves multiplying by x2. And so when we look at the code, you've got Y bar multiplied by x2. The incrementation by 0 is effectively, in reverse mode, you sort of keep incrementing different things, keep it added onto the derivative, but we'll see a little bit more on that later. Basically, here we've got xb1 equals this quantity, and for xb2 we've got the other quantity, which when we go back to the DAG, you see that we've got Y bar coming in as the seed, and then we want to compute the second component, so all we're going to do is multiply it by the first component. Has anyone got any questions? I remember when I first saw this, I was completely baffled why the forward mode and the reverse mode look so different. But when you sort of dig into what's going on, it's all the same operations, right? We've got a multiplication by the second component and a multiplication by the first component. It's just being presented in a different way.
What's the function buffer to set YB similar?
Yeah, so I think you can configure Tapenade not to do this, but by default it will always reset the seed back to 0. I think in practice this is because it might even be a comment on this actually shortly. In practice, this is usually the right thing to do when you run this sort of in production. Because you don't tend to do the same propagation twice, and if you do the same propagation twice by accident, then you can start to accumulate gradients that aren't correct. But yeah, for these kind of simple examples, it doesn't confuse things, I find. So yeah, you will always find in reverse mode that Tapenade will 0 the seed at the end. Of course, that doesn't affect the gradient that's being computed here. Provided that YB was non-zero initially. So it's just scrolling down. So we should see, this is what we've just been looking at. And then we can do the same thing for G as well. So if we just change, we change the code slightly. So we need to put G, and then we need to update the arguments for the function. And then now we've got GB, which this one I think maybe looks slightly more what you might expect. But I'll leave you to be the judge of that. So in the first component, well, so YB only has one component because it's just a scalar. So going back to the DAG again, we're going now from Z to Y. So we take two different seeds, Z1 bar and Z2 bar, and we're going to propagate to get Y bar. And so for the first contribution, we need to take the derivative of sine and multiply it. And then for the second contribution, we need to take the derivative of cos and multiply that. And these are both going to get added together because there's only one output. And so when we go here, you see for the first component, we've got Z bar 1. So it's the first component of seed multiplied by the derivative of sine. And then for the second component, you've got the second seed multiplied by the derivative of cos, which is minus sine. Yes.
Going forward mode, the derivative of y that's returned is sum of the derivatives for the derivatives.
Yes, so let's have a look at that one as well, shall we? So E tangent D. So if we look at this one,
I mean f mod d. F mod,
oh, F mod D,
yeah, I'm still on the y.
F mod D. Okay, so this one here,
YD, yeah.
yeah. You're saying that this one looks very similar
So
to
I'm saying that
this one.
this one is the sum of the two first to the partial derivatives.
So this is where we're starting to see here the similar behavior for when you have different, well, when you have different numbers of inputs and outputs. So F has two inputs and one output. And so when you do forward mode, you have two inputs and one output. Well, sorry, the seed has dimension 2 and the gradient has dimension 1.
Yeah.
And then when you have
Dot product.
the dot product, yeah. Yeah, gradient is kind of used in a misleading way sometimes. Whereas with G, its input is dimension 1 and its output is dimension 2. So when you do the reverse mode, the seed is dimension 2 and the derivative is dimension 1. So you start to see that if the numbers of inputs and outputs are the same, then it starts to look quite similar. But yeah. Has anyone got any other questions about this sort of exposition with reverse mode? If not, then we can carry on and actually use it. So, as I said, it can be very confusing why these things look so different. And so what we're going to do is we're going to verify that they give the same thing, just in a different format. So yesterday we saw the Taylor test, which was a numerical way to verify that the gradient was accurate, or the directional derivative was accurate. Today we're going to use the dot product test, which is not a numerical approach. So we've been having this notation of dots and bars, and so we'll continue to use it here. So when we have forward mode, if we have x dot as the seed, then the JVP can be written this way, where y dot is the output. So let's just, given some function and some input and some seed, we've got this quantity. And then given the same function and the same input, and then another seed, but for the reverse mode, we have this quantity here. So x bar transposed is equal to this thing. I don't know if it should be transposed there, actually. Sorry. Apologies. That shouldn't be transposed. To be copied and pasted, unfortunately. So we've got these two quantities here. So JVP, JTVP. So let's define phi to be y bar transpose y dot. So it's a vector transpose another vector, so it's like an inner product sort of thing, dot product, which is why it's called dot product test. So y bar is a seed that we're just choosing arbitrarily. And then y dot is the derivative that's computed using the GBP. So I'll leave it as an exercise to the reader to check that we actually expect phi, the same value of phi to equal x bar x dot. So I can now see where that transpose was meant to be. It was meant to be there. So the dot product of y bar and y dot, we should expect that to be exactly the same as the dot product of x bar and x dot. I mean, maybe people do actually want to see this. People want to see this working. Oh no. It's basically just substitution. But we can show that if we just substitute the definition of y dot in here, we've got GBP, and then when you've got these kind of expressions, they are associative, so you can move the brackets around. It's fine. And then this expression here in the brackets can also be written in this way. So you take the transpose twice basically to get the same thing. And then it's just the same as the definition of x bar. So it's just a bit of rearranging and substitution, but this sort of proves that we do expect these two things to be equal. And so what we do in the dot product test is we compute both of them and check they're the same value. And if they are, then the AD tool is correctly, well, we don't necessarily know that the AD tool's actually got the right answer necessarily, but at least it's computing the forward mode and the reverse mode in a consistent manner. So we've got a bit of code here, which again is written in Fortran. It will pull in the derivatives that we've computed for f, both for the forward mode and the reverse mode. So if you didn't do what I did just before and also run the forward mode, you'll need to do that again, like we did yesterday. And so we take some, hopefully the comments make it clear, but we've got some input for f itself, the primal code. We've got some seeds. So in this case, we've got a seed for the forward mode and a seed for the reverse mode. And then we've got the reverse mode derivative and forward mode derivative. So yeah, it's maybe in a slightly confusing order, but these are all the things we're going to be working with. And we want to check that the one product is equal to the other. So there's result one, result two. This is tolerance because this is, at the end of the day, we're evaluating on a computer, so they're not going to be exactly the same. But we have this, the first computation here is to take some arbitrary primal input. So this is just some numbers that I put in there. In some cases, you might need to be careful what exactly you put. So if you're evaluating a 0, it might all kind of go wrong. Or if the function isn't actually differentiable, then of course you'll have problems. But this is just some fairly arbitrary input for this simple function. And we also have a fairly arbitrary seed as well. And we can evaluate that FD. And then we choose a seed. So here we've made a few choices. So there's a choice of input, there's a choice of seed for forward mode, and there's a choice of seed for reverse mode. And then we can compute the dot products of YD and YB. And that's the one thing that we want to compare. So that's psi, as we defined above. And then for the reverse mode, this doesn't look right. Why is that clear? Maybe it's just getting 0 beforehand. Well, in either case, we need to choose we've already got the seed for reverse mode, because that's YB that was defined above. That's going to be coming in, X is going to be coming in. And then XB is what we're going to be evaluating. and y is the output of FD. So we compute this other thing, and we check that they're equal down the bottom. There's just some code that will do that. So we'll give a few minutes for this exercise. So as I said, you'll need to regenerate the forward mode derivative for f. And you'll need to build and run the dot product test, which is just, you just need to type make dot product test. And then if you finish that and you've got a bit of time, then you can play around with moving these lines of code around and seeing why sometimes things break. So yeah. Yes.
Is there any particular reason why B has three? And it'd be like one. I mean, X
yeah.
is finite.
Yeah, yeah.
Like understand it's gonna be 0.
Yeah. So the question is, why did I choose X? B is 3. It was just arbitrary, basically. So as you point out, when you do reverse mode, or when you do either of the cases, and there's only one argument, sorry, when the seed only has dimension 1, you should probably just choose 1, because that then the derivative that you get won't be scaled. It will just be sort of normalized. But again, yeah, as I said, it's just an arbitrary number. You could choose y equals 1, hopefully it'll still work. Okay, so in the interest of time, we'll press on. So we've already regenerated the forward mode derivative, but if you want to see how to do that, you can click the solution. We can then type make dot product test. Unfortunately, didn't do what I expected. And then we'll have this dot product test executable. We can run that and we should just get pass. Did anybody have a go at the third optional one by any chance? Yes, what did you find? Do you know why it failed?
Against why B gets set to 0 by the NB. So dot product.
Exactly. Yeah, so Sam pointed out that if we change the order of these lines, you've got to be careful because in the reverse mode, as we noted before, this YB would be set to 0 at the end. So unless we figure out how to turn that behavior off, you just got to be aware of that. This YB is being treated as this number. Good. So we've got one more example with tapenade, and then we'll look at the operator overloading. So just as a refresher, we've got the JVP and the JTVP. We've been computing these first order derivatives. Does anybody have an idea of a way that we can compute the Hessian? And the Hessian is the matrix of second order derivatives. So if you've got n partial derivatives, then this comes out as being an n by n matrix, where the ijth entry is the ith partial derivative. Sorry, the second derivative that's both the ith and the jth component. Does anybody have any ideas about how to do this? Yeah.
Could you repeat the process so that you take the derivative for the derivative?
Exactly.
Yeah.
Exactly. The fact that I've said there's 2 ways, I mean, this is more of an implementation question. So yeah, at some point out, we can do this by applying tapenade to the thing that it just produced. And there's 2 ways we can do it. We can either apply forward mode and then forward mode again, or we can apply forward mode and then reverse mode. So we're going to do that for the Spielpenning example. So again, I mentioned that Spielpenning is kind of a big name here. So Spielpenning introduced this test case where it's just a reduction that through multiplication. So you take a function where it has a vector of input and it just multiplies all of the components together. So this is actually a more general case of the function f we were looking at before. So f is just the 2 arguments multiplied by each other. This one is you multiply all of the arguments together. And the reason this is interesting is because it's dense Hessian. So we've got this code here that implements it. It's just a loop over different components multiplied by together. So the exercises are to compute the Hessian of this function using tapenade in forward mode twice. So we apply forward mode to get a derivative, and then we apply forward mode again to the derivative code. And it's worth noting that there's several, it's a vector input, so you're going to need to use vector mode. And once you've done that, you can then build and run this new Hessian program, which will print the Hessian to the screen. And then there's also some optional exercises where you can derive the expected Hessian by hand and convince yourself that you've got the right answer. Again, I've sort of left the ones that involve maths out, but if you fancy doing that, you can do. And the solution is below. And then if you're feeling ambitious, then you can try doing forward mode and then reverse mode. There's a hint as well that you'll need to use when you do the second derivative. So we'll give a bit of time for this one because I know it's a little bit more advanced. But hopefully it's still doable. Any questions about this exercise? Okay.
Would you have two C factors?
Yeah, it's a good question. So Sam asked the question, do you need two C vectors? So yes, you do. So I should have mentioned that for the first application, you're going to need a C vector, and then for the second one, you're going to need one as well. So you can kind of think of this as having one vector transpose Hessian and then the other vector. So because you're, well, it's actually not vector, it's the vector mode, isn't it? But basically you need, you do need to have directions for both of them. I think we did already see this diff sizes thing yesterday in the sparse mode. So when we were doing the sparse example, we were using vector mode, and we needed to define this diff sizes module that it specifies the number or the maximum number of seed vectors that you're going to use. This is just something that tapenade requires. So this is what we saw yesterday, where for the dense case, we had the number of directions being equal to the number of variables, which was 10. And then in the compressed mode, we just had 3 because we could get away with using 3 seed vectors. And so today we've got these 2 different modules. So there's diff sizes gradient, and I've just chosen fairly arbitrarily to have 7. Like we're computing the product of just 7 values, 7 arguments. And then for the Hessian, it actually requires the second value. So this is what we were just talking about. We need 2 seed vectors, so or 2 seed matrices. So for the first application, it's going to have dimension 7, and for the second one, it's also going to have dimension 7. And that's so we're going to have this. In this case, it's a scalar function with several variables. So the Hessian is going to be square. I mean, Hessian's always square actually, but you can get other matrices of second derivatives that aren't square. Is kind of the thing there, but we won't consider those. Okay, so we'll go through the solutions here. Did anybody manage to generate a Hessian? Yeah, a couple of people. Nice. So the first thing is very similar to what we saw yesterday. So we're in the spiel penning example, and we type tapenade -d. We want vector mode. We want this tangent module name to be _d, to avoid confusion between forward mode and reverse mode. And then we just put spiel penning as the subroutine name, and then there's independent variables x and dependent variables f. We give it the file name, and it will compute this derivative. Again, it's got dv because it's vector mode. And when we look at this thing, as we saw yesterday, it computes the function f eagerly. So it starts off with value 1 and then multiplies by each component. And then for the derivative, it does some extra stuff, which, as you can see, is effectively just applying the product rule to each of the components. And then to get the second derivative, oh, sorry, this solution is to show what I've just shown you. As I mentioned before, we need to now specify the numbers of directions. And to get the second derivative, we can take a very similar thing, but let's just work through how we're changing this prompt. So we've got tapenard -d because we're using forward modes for a second time. We're using vector mode again. We're using this tangent module known as the same thing. But then now, instead of applying it to spiel penning, we're applying it to spiel penning dv, which is what we just generated. We're still computing derivatives with respect to the input x, so we can leave that as it is. But now, the thing that we're differentiating is now fd rather than f. And apologies again that there's this arbitrary ordering here. You can do it in the same way as what's shown in the solutions. And instead of having spielpenning.f90, we need spielpenning dv.f90. And the final thing to note, as I mentioned in the hint, is that we need to also tell tapenard about these maximum numbers of directions from the module diff sizes, so you need to put that in the path as well. And you can see that it generates this now spielpenning dv, which we can look at, and now it's going to start getting very complicated. So again, it's using this diff sizes module. It uses it twice for some reason. And you can see that when we do the second application, it starts putting boilerplate in for a second time as well. And this also started to get slightly confusing to read because this was the original docstring. This is the docstring for the forward mode. This is the docstring for the second forward mode. So anyway. And we can see now that this function has x as an input, and then we've got two different seeds, as we were talking about before. It evaluates the function itself eagerly, it evaluates its gradient, and it evaluates its Hessian. So all in one function, you get to evaluate all of these different things, which is kind of nice. And then we have the numbers of directions for each of them, which in practice is just going to be the same. But as we look through the code, as I said, it's getting quite complex now, but at the end you see the function evaluation, and then here we see the gradient evaluation, and then here we see here we see the Hessian evaluation. And we can then run make view Hessian without the .f90. You can run it, and you see that there's this matrix that gets printed here. Anyone got anything interesting of note about this matrix that they observe?
Euros.
Yeah, the zeros on the diagonal. Is that?
And symmetric.
It's symmetric, which is what we expect. Hessian matrices are always symmetric, so that's good. And there's also these zeros on the diagonal. And we think, well, that seems a bit odd. Is that correct? If we look back at the function, then for each of we're always computing partial derivatives with respect to each component. And it's linear in each component. So yeah, the second derivative is 0, exactly. So if you take the second derivative with respect to the same component twice, you're going to get 0. So this is actually expected. The diagonal would be 0. And then whether or not the off diagonals are 0 depends on whether that value was 0 in the first place. So in this case, none of the values were 0. If you look into the source code for this view Hessian, none of the values were 0. I think it was just 1, 2, 3, 4, 5, 6, 7. And so we do actually expect that the off diagonals won't be 0. And if you do the optional exercises, you can prove to yourself that the other numbers are what you expect. Cool, so we've not got loads of time left, so I'm quite keen that people see operator overloading. So we should move on to that. Now, operator overloading is a fundamentally different approach. And the reason that we did source transformation first is that whilst it can get quite complicated, hopefully you will agree that you can see the derivatives that are being generated. So it's got a line of code and it shows the derivative for that line of code. And so we can kind of, whilst it's a bit of a black box in terms of how it's done it, I've not explained that to you. You can at least see what it's generating. Operator overloading is a little bit different because that is just fully like a black box almost. I'm going to show you tell you how it works under the hood, but you don't really see any code that's been generated. You just see the inputs and the outputs. So as I say there, it doesn't generate any source files. It actually computes the derivatives at runtime. So everything we've done has been as a pre-processing step. So you have some code, you generate the derivatives, then you compile the code, and then you run it. In this case, we take the code that we have, we compile it. Well, I mean, you have to make some edits to it, but then you compile it, you run it, and when you run it, that's when it generates the derivatives. So it's a very different approach. And the general idea is to record all of the operations that have happened to all of the variables, and then process through all of the record to say, well, what's the derivative and how do these track with the chain rule? So depending on the AD tool that we have, the user experience is something like this. So firstly, we edit the code. So this is the code that you're going to run, not this separate derivative code. The same code file. We go in and we mark which of the variables are independent variables. So we've been doing that before because we've been specifying to Tapenard, okay, differentiate with respect to this. In most AD tools, you also need to say what the dependent variables are, but for some of them you don't, it just detects automatically. And again, with Tapenard, we've needed to do this, but we do it at the command line rather than editing any code. We need to put in driver methods. So like the AD tool will provide like a compute gradient function or like a compute Hessian function or whatever. And you need to call that. And then finally you run it. So there's some code modifications and then you run it, and that's when it actually computes these things. So we'll take a little step back. What is operator overloading? Because people might not have heard about it. Who's aware of operator overloading as a concept? Okay, so maybe half of the room, something like that. So operator overloading is it's something that fits very well with this idea of a different OO, which is object orientation. So in object-oriented programming, you work with classes. So Python, for example, we work with classes. Like Python is sort of object-oriented all the way down, but you can do object-oriented programming in Fortran in more recent times. You can do object-oriented programming in C++ and in lots of other languages. And the idea is you've got a class, and it has both data and it has methods. And so this is how you define a class in Fortran, or a derived type as it's called. So we can define some class, and then we can define how you do operations on it. And those operations can include addition, multiplication, division, blah, blah, blah. And so it's kind of like what we saw in the last course with Matt and Isaac. They had to define like the length method for the class that was being defined. This is a case of operator overloading, where you use this a common way to call some functionality, and it means different things depending on what you apply it to. So if you've overloaded the addition operator for your class, then you can say C equals A plus B, where A, B, and C are all instances of that class, and it will do whatever's been implemented. And so similarly, if we define a class that has two values, it's got a double precision value for it's just called value, and it's got a double precision value called grad, which is the gradient or the derivative value. Then if we overload the operators for this class, then we can compute derivatives at the same time as computing just the standard values. So for addition, it's easy. So addition, if you've got two different of these A doubles, as I've called them, it's quite a common name in literature, then you just add together those two values. And if you add together two A doubles, then you also add together the two gradients. So it's like these two operations at the same time. And this is called like the primal, it's not primal, it's called the dual number approach. So yeah, in forward mode, it's sufficient to just overload these operators. And so you set your seeds as like the initial values of whatever's the independent variable. So for that, the gradient attribute of that independent variable, you would set it equal to 1 or whatever the seed vector is. And then as you do your computations in your program, it's going to automatically compute the gradient at each of these steps. But then if you need to change the seed vector, then you're going to have to start again. So this is where, like with forward mode, you potentially need to do multiple runs if you have multiple different independent variables. For reverse mode, it's not sufficient. So in reverse mode, we as I said before, we need to run the program, and then also run its before we can then run the reverse mode. And so there needs to be some sort of memory of the state as you go through the code. So the way that this is done is with something called the tape. It's the sort of standard name that's used in the literature, probably for historical reasons, I guess. And basically, it just becomes a record of everything that's happened. So for this bit of code here that implements the test case we've looked at quite a few times now, it's just 2 assignments and a multiplication. Then a sort of conceptual version of the tape would look like this. So we first have an assignment of 2, and the output is x1. Let me see if I can get them both from the same thing. There we go. So we record this in this way. We record that in that way. And then for the multiplication, now there's 2 dependencies. So it depends on both x1 and x2. And we have 1 output, which is 1. This is not how it's done in practice. This is just like a very simple sort of sketch of how you could think about it. But it's just a lot of bookkeeping to track what happens. And the fact that we're using this overloaded type means that we can set it up such that entries are added to the tape as we go through the program. It's kind of the idea. And then once all the entries have been added to the tape, you can just unroll the tape to then replay what's happened. So you can then give it different inputs, and you basically have a separate implementation of the code that can just be read from the tape. Now, I said they use the term unrolling. That's the common term to unroll this tape. And in forward mode, as we said, we could either use this dual number approach where we just sort of on the fly compute these gradients as we compute the primal code. You could also write it to the tape and then unroll the tape. What do you think is the difference between the forward mode and the reverse mode as far as tape unrolling is concerned? Any ideas? It's not a trick question. Like just based off of the names, what do you think?
Direction.
Exactly. It's in the reverse mode. So we instead of reading the tape in the forward direction, we read the tape in the reverse direction. That's all it is. Because you're taking perturbations in the output and then tracking backwards to get the perturbations in the input. That's all it is. Just going backwards through the tape. And we're going to use a tool called PyJoint, which I won't go into in a lot of detail, but it's already been installed into your instance. And the reason I picked PyJoint is because it's a tool I've used a lot before, and you can interrogate the tape quite nicely in that. So in some of the other AD tools, it's not quite as straightforward how to do that. So I've implemented a function here, which is going to print whatever's on the tape. So as you might expect, PyJoint is implemented in Python, so it's all going to work within the notebook now. We don't need to jump around and look at Fortran code, so I can probably close that. So there's this function that will go through the tape and print whatever's on there. And then, as we saw before, whilst this can be represented as a list maybe isn't the best way to do this, because there could be separate parts of the code that are doing separate things and they only come together later. And in this case, it's kind of the opposite, where the code, well, I suppose these are separate. You've got 2 separate assignments and then they come together later, right? If we reordered index 0 and index 1, it wouldn't make any difference. You still have exactly the same output. And so perhaps a better representation is to use a DAG, or a directed acyclic graph, like we've seen before. And PyJoint has the ability to do this with network X. So I've written a bit of code there that will plot the DAG as well. So it will just take whatever's on the tape and it will plot it. So we're returning yet again to our favorite function, product, and it's now implemented in Python. So if you go through and execute that, then we're going to be doing operator overloading here. So we've not done anything just yet. We've defined a load of functions. The first thing that you do in PyJoint is you start the annotation. There isn't a start annotation method, it's just a continue one, because you can pause and continue. But this is the notation that they use for saying, okay, we're now in a part of code that we want to differentiate. So that yesterday I used the term active, so there's active and passive. We're entering an active part of code, and we define two variables, x1 and x2, and they're defined using add float. So before I use the term a double, just because it's quite common in the sort of older literature, but in because in Python we have floats, we have this term add float, and add is adjoined, like we said before. And this is basically just a class which has overloaded the operators that you would find on float. So you can do addition, multiplication, both. So x1 is one of these add floats, and it's just a number 2, and then x2 is one of these add floats, so it's just a number 3. So we can execute that, and then, as I said, it's overloaded the operators. So f includes a multiplication, and if we run this cell, it's going to run the overloaded multiplication operation, and so it's going to do some more stuff behind the scenes. And if we interrogate the tape, print it, and you see that okay, there's some entry which has said there's been a multiplication. Note that it doesn't mention the assignments here, so depending on the AD tool, they may or may not print this kind of thing out when you view the tape, but it doesn't know what the values were because that's encoded within the tape in PyJoint. And then when we plot the DAG, as I said, we've got two different things, so two assignments. You've got the product, and then you've got the output. And apologies, it's not consistent how it's when you print the tape or you view the DAG, it includes the assignments or not. But we can see that this is kind of what's happening. Two things are coming together, and we're getting an output. When we finished, we can say, okay, we're now in a passive part of the code, and so we can pause the annotation. So if you continue to do any further operations on these variables, it won't record those. To declare the independent variables, we do it this way. So we specify them as controls using the sort of optimization terminology. So x1 and x2 are both controls, i.e. the independent variables. And then, as mentioned before about like driver functions, so PyJoint has this compute gradient driver function. So this is effectively the JDP. So we want to compute the JDP of the output y, so y equals f of x, evaluated at this value of x. And it's implicitly chosen the seed to be 1. It just happens on the hood. And so we can compute this dy by dx. And you should see, well, firstly, it prints out the doc string for a compute gradient in case anyone's interested. And then you can see here that x was equal to 2 and 3. Y was equal to the product, which is 6. So we're happy with that. And then dy by dx is equal to 3, 2. So if you look at how this was written, it's sort of a check that this is what we get as the output, dy by dx, first and second component. And then this is what we expect. So this is if we do the derivative by hand, what we expect, and they are indeed the same. So we're running out of time, so I'll kind of just leave you to play around with these things. You can take a look at, well, firstly, think about what you expect the Hessian to be. And I think perhaps we already know the answer because we saw the general case before. And then experiment with using the driver function for computing the Hessian. So it's just called PyJoint.compute Hessian. So I'll leave that as an exercise. And then just sort of wrap up. So we've seen source transformation versus operator overloading. We've already discussed a lot of these details, but differences. One thing to note is that operator overloading requires memory for the tape. So if you're going to store, you store what's happened, but you also store the states as well. And when you start having big problems, with large arrays and stuff, this can start to require a lot of memory. And so you need to think about how to do that in an efficient way. There's some details below on checkpointing, which we won't get to. But if you want to read that in your own time, then that will give you a bit of information on how to use this in real world problems. So in source transformation, we saw that there are only a handful of tools, and Tapenade was probably the best one for us to work with. For operator overloading, there are so many tools. So in C++ alone, there's about 24. In Julia, there's about 24. Apparently, because it's so easy to implement operator overloading AD in Julia, it's almost as you could, if you know what you're doing, you can do it in an afternoon or something. It's very well set up for that. So a lot of people have given it a go. One of the interesting cases is Enzyme, which actually does the automatic differentiation in LLVM. So in theory, this could actually enable automatic differentiation in all sorts of other languages as well. But that's work in progress, and I think they're mainly working with exposing in Julia at the minute. There's these domain-specific ones, like what I just mentioned, PyJoint. There's various Fortran ones, including a lot of abandonware. PyTorch has its own tool, but unfortunately, you can only do reverse mode, not forward mode, which is why we didn't use it today. JAX, you've probably heard of, and others. And one thing that I really wanted to mention, because I think this is quite important, is the level of abstraction. So we've in this whole course, we've been working on elementary operations applied to just like entries of vectors and entries of matrices. This is often not the right thing to do. So if you have a linear solver, it's got so many different operations. Like you iterate over matrices, and you like iterate over other matrices, and you do all sorts of combinations, these kind of things. If you differentiate through every single operation, the tape's going to be really, really long. It's going to be very, very hard to read. And when you compute the derivative in source transformation mode, it'll be very, very hard to read, probably. If you look at it in operator overloading mode, the tape's going to get quite big. And so sometimes the better thing to do is to take a step back and use a different level of abstraction. So one option is to look at API calls. So if you have a matrix times a vector, then it's quite easy to figure out what the derivative of that is. When you do forward mode, it's one thing, and then when it's reverse mode, you have a transpose. So there's some work that's been done recently in PETC that does this. So it takes all the different PETC is a C-based solver library. It takes all the different API calls and differentiates each of them so that when you do the automatic differentiation, it stitches those together and only records these higher level operations rather than all the lower level ones. And then even higher level than that, there's PyJoint, which we just had a look at. It works on these edge floats, but it also works on higher level constructs like fields. So if you have a field that's like the solution of a partial differential equation, for example, that's being solved in Firedrake or Phoenix or some other finite element library, you can actually do the automatic differentiation on that level. And that works out to be quite nice. So if you have time to play around with some of this stuff, you'll see that there's some Firedrake examples that have been pulled in from their documentation. So there's this PDE constrained optimization one, which is particularly nice. You can work through that. There's a bit of finite element stuff that you might need to take on board, but you'll see that the tape only having like 10 or 20 entries, you can do a PDE constrained optimization problem. So this is, Firedrake is great for prototyping and for research type stuff. So when someone said yesterday, how can I actually use this in my work? I think this is one of the cases where you can do. So I realize we're over time now, so I should wrap up. There's loads of stuff you can read. Checkpointing. So yeah, hopefully you've learned about reverse mode, operator overloading, and played around with those, both with Tapenade and then with the PyJoint tool. And then there's further information on checkpointing and for higher order derivatives. So thanks for listening, and I'm happy to chat over lunch or throughout the rest of the week.